these examples go with section 7.4, vectors. This is part 2. Example 8. A ball is thrown from a height of 1 meter. At the time of release, the velocity of the ball is given by v is equal to 27.2 I plus 12.7 j, where each component is given in meters per second. Find the initial velocity v0 and the angle theta above the horizontal in degrees at which the ball was thrown round to 1 decimal place. All right, the initial velocity is also known as the magnitude. So let's see if we can figure out the magnitude of our vector. And that's going to be the square root of 27.2 squared plus 12.7 squared. This gives me the square root of 901.13. And if we square root that in the calculator, we're going to get 30.01, but since we're supposed to round it to 1 decimal place, we're just going to leave it at 30.0, and this is going to be meters per second. Now the angle we can find just by using the inverse tangent. And remember, that's going to be y divided by x, or in this case, 12.7 divided by 27.2. When we put this into the calculator and round to 1 decimal place, we get 25.02, but again, we're rounding to 1 decimal place, so we're looking at 25.0 degrees. Example 9. Joe enters a triathlon and must swim to a buoy offshore and then back again. A current of 0.5 miles per hour flows due west. Part A. If Joe starts at the closest point on the shoreline to the buoy, in what direction theta should he swim in order to arrive at the buoy? Assume that Joe's speed of swimming in still water is 2.5 miles per hour, round to the nearest tenth of a degree. Part B. What is Joe's true speed, round to 1 decimal place? Okay, let's take a look at what's going on here. If we place Joe down here on the shore, without the current, he would be able to swim straight across to the buoy. However, there is in fact a current, and the current is swimming due west, which means it's going that way. And so in order to get to the buoy, Joe's actually going to have to swim in this direction, because eventually the current's going to be pulling him this way until it actually looks like he in fact has swam directly out to the buoy. So he's going to be swimming against the current. Okay, so over here, this would be Joe's true speed, okay, which we don't know. And we'll call that K. Alright, and we're just going to call this V sub 1 for the vector. Okay, so for speed here is K. The angle that he would be swimming, if he were actually able to swim straight from the shore to the buoy, is going to be 90 degrees. And so if we put this into terms of I and J, we're going to have something that looks like V1 is equal to K times I times the cosine of 90 plus k times j times the sine of 90. Now, the cosine of 90 I know. This is going to give me k times I times 0 plus k times j times 1. And so anything times 0 is going to give me 0. So I actually have 0i plus kj. So this vector over here is 0i plus kj. All right, our current vector is right here. And the current speed is 0.5. And the angle that the current is flowing, this is going due west. And so that's 180 degrees or pi radians. And if we want to put this in terms of I and k, then our v2 vector is going to be 0.5 I times the cosine of 180 plus 0.5 j times the sine of 180. All right, so I know the cosine of 180, this is -1, and I know the sine at 180, that's 0. -1 times 0.5, this is going to give me -0.5i, and of course 0 times 0.5 is going to give me 0, so we actually have 0 j's right here. So in its terms of I and j, our vector here is going to be -0.5i plus 0j. Okay, now Joe right here, this is our vector 3, is going to be a little bit trickier because we don't know what his velocity is. Well, we don't know what it is in still water. I'm sorry, let me rephrase that. We do know what his velocity is in still water. So if he were not fighting the current, he would be swimming 2.5 miles per hour. All right, so in still water, we know his velocity is 2.5 miles per hour. We have no idea what angle he's swimming at. In fact, that's kind of what we're trying to figure out, what angle he actually has to be swimming at in order to fight the current and still meet up again with the buoy. And so putting our vector 3 into terms of I and j, we're going to have 2.5 times I times the cosine of theta plus 2.5 times j times the sine of theta. All right, now I'm going to move over to the next slide and get a little bit more room. All right, so here's our picture. I've drawn it again on our next page here. Now, according to vector addition, now let's take a look at the arrows here, okay? If I do the head to tail addition, I'm adding vector v3 plus vector v2. That should give me vector v1 right there. So v1 is going to be equal to v3 plus v2. Well, v1 is equal to v3, we said was 2.5i times the cosine of theta plus 2.5j times the sine of theta. And then v2, we said that was -0.5i plus 0j. All right, let's simplify that a little bit. We're going to have 2.5i cosine theta minus 0.5i plus 2.5j sine theta plus 0j. Now, this part right here is just going to cancel out, so I really don't need to have that in there. And I also have a vector for v1. We said it was 0i plus kj, so let's fill that in too. We got 0i plus kj equal to 2.5i times the cosine of theta minus 0.5i plus 2.5j times the sine of theta. Okay, and now we're going to be a little bit clever here. I'm actually going to create some like terms. Now, remember what we did last semester with the partial fraction decomposition? Okay, I'm actually going to make an equation out of the 0i, the 2.5i cosine theta, and the negative 0.5i. And I'm also going to make an equation out of the kj and the 2.5j sine theta. And so that's going to look like this. We're going to have 0i equal to 2.5i cosine theta minus 0.5i. And I'm also going to have kj equal to 2.5j sine theta. So now I have a system of equations here. All right, let's take a look at this first one and see if we can do anything. If we simplify this and pull the i's off, we'll have 0 equal to 2.5 cosine theta minus 0.5. Okay, now if I want to solve this for theta, I'm going to add 0.5 to both sides. Now I have 0.5 equal to 2.5 times the cosine of theta. Right, we're solving for theta. Let's divide out that 2.5 on both sides. That means the cosine of theta is actually equal to 0.2. And if the cosine theta is equal to 0.2, then theta must be equal to the inverse cosine of 0.2. And that gives me 78.5 when I round it off to the nearest degree. And so the direction that he needs to be swimming, our theta there, is going to be 78.5 degrees, right? So there's part of our answer. That was actually part A. We just found theta. Okay, B. Now we want to find his true speed. In other words, now that we know theta, we need to solve for this side of the equation here. Actually, we're just going to plug it in here and we're going to find K, because we said that was going to be his true speed, because here's the true speed right here. Okay. And again, I'm going to pull the J's off of there. So let's see, we got K equal to 2.5 times the sine of theta. That means K is equal to 2.5 times the sine of 78.5. And if we put that in the calculator, 2.5 times the sine of 78.5, it gives me 2.4. And this would be, I think, yeah, in miles per hour here. So he's actually swimming 2.4 miles per hour at an angle of 78.5 degrees. That'll take him along this path right here, and then the current's going to wind up carrying him back over here to where the buoy is located. Example 10, if the magnitude of F1 is 32 pounds, the magnitude of F2 is 24 pounds, and the magnitude of F3 is 15 pounds, write the resultant force R in terms of I and J. The resultant is the sum of the forces acting on an object. So really, R is going to be equal to F1 plus F2 plus F3. Okay. All right. This is going to be our force right here. So this is going to be our magnitude for force 1. This is going to be our magnitude for force 2. And then this one is going to be our magnitude for force 3. Now we just need to know what our angles are. Force 1 is pulling straight up. That angle is 90 degrees. Force number 2 is actually this angle right here. Now I know it says 68, but it is pulling in this direction. So this is going to be 90 plus that 68, which is going to give me 158 degrees. And then for force 3 down here, the angle, and again, it's going to start here and it's going to come all the way around. So I know this says 40 degrees, but the actual angle that we are exerting force on is going to be 360 minus that 40 degrees, or 320 degrees. Okay? So force 1 in terms of I and J is going to be 32 times the cosine of 90 times I plus 32 times the sine of 90 times J. Force 2 is going to be 24 times the cosine of 158 times I plus 24 times the sine of 150 times J. And force 3 is going to be 15 times the cosine of 320 times I plus 15 times the sine of 320 times J. That means our resultant here, this is going to be a long one, R is going to be 32 cosine 90I plus 32 sine 90J plus 24 cosine 158I plus 24 sine 158J plus 15 cosine 320I plus 15 sine 320J. And now we would just add our like terms. That means we'll have 32 cosine 90I plus 24 cosine 158J plus 15 cosine 320I plus 32 sine 90J plus 24 sine 158J plus 15 sine 320J. Okay, now we need our calculator so we can get all these together. Okay, so when I put this first set of parentheses into my calculator, it gives me negative 10.8. This is when I round off to one decimal place, so this is I. And then when I put the second set of parentheses right here into the calculator, it gives me 31.3 J. And so this is my resultant. This is the sum of what I get from those three forces acting with each other. Example 11. Two cranes support a 2,000-pound beam in static equilibrium. Find the magnitudes of the tension vectors T1 and T2. The direction angles for T1 and T2 are 45 degrees and 120 degrees respectively. Round to the nearest pound. Okay. You'll notice in the picture that the angles have been labeled as 45 and 30. Remember, this angle over here came about because we actually have a 90-degree angle here, and 90 plus 30 is going to give you the 120. So that's where that had come from. Okay, we have the vector given down here, 0i minus 2000j. We could write that in terms of the sine and cosine. The magnitude here is 2000, and our angle, because it's pulling directly down, this is 270 degrees. So we got 270i plus the sine of 270j. All right, and T1 over here is going to be equal to the magnitude of T1, whatever it happens to be, times the cosine of 45 degrees, plus, again, the magnitude of T1, whatever it happens to be, times the sine of 45 degrees, and then j. And over here, T2, this one's going to be equal to the magnitude of T2, whatever it ends up being, times the cosine of 120 degrees times I, plus the magnitude of T2, again, whatever it ends up being, times the sine of 120 degrees times j. All right, now I'm going to take these equations and I am going to put them on the next page. All right, so I've written all of our vectors up here across the top. And now, because the problem tells me that these forces are all operating in static equilibrium, I know that if I add this vector plus the vector T2 plus the weight vector over there, we should get the zero vector, or 0i plus 0j. And so what I'm going to do is I'm going to set up that equation right here, substituting what I know T1 is equal to, that's all it's over here, and what I know T2 is equal to, and then what I know W is equal to. All right, that's going to give me this equation. And what I've done is I've separated each one of them by parentheses so you can tell where T1 was and T2, and then the W vector back here. Okay, the next thing we want to do is we want to separate this into two equations. I'm going to have something called the I equation and the J equation. And I'm going to take all of the terms that have an I in them, and I'm going to make one equation with it. And then I'm going to take all the terms that have a J in it, and I'm going to make another equation like this. And I put my I equation over here on the left, and I put the J equation over here on the right. And now what I'm going to do is I'm going to use the unit circle, and I'm going to simplify some things, because I know 45 degrees is on the unit circle, and I know what the cosine is. And 120 degrees is on the unit circle, and I know what the cosine is. And 270 is on the unit circle, and I know what the cosine is. And likewise over here with the sines. All right, and this is what we have. We have the equation. We got the magnitude of T1 times the square root of 2 over 2 plus the magnitude of T2 times negative 1/2 plus 2000 times 0 is equal to 0. And over here we've got the magnitude of T1 times the square root of 2 over 2 plus the magnitude of T2 times the square root of 3 over 2 plus 2000 times negative 1 is equal to 0. And I guess this should really be 0j, but I think I'm just going to take the i's and the j's out of there for the moment to try and eliminate some of our confusion here. All right, now let's see if we can simplify this a little bit more, because I know this part right here is just going to cancel out because 2000 times 0 is just 0. And so that's just going to leave me with the magnitude of T1 times the square root of 2 over 2 plus the magnitude of T2 times negative 1/2. And this is going to be equal to 0. Over here, we're going to have the magnitude of T1 times the square root of 2 over 2 plus the magnitude of T2 times the square root of 3 over 2. And this is going to be minus 2000. This is negative 1 times 2000. Okay. All right. Over here on this side, I'm going to work a little bit. I'm actually going to eliminate the fractions. And then I'm going to solve for one of my variables, and then I'm going to substitute into this equation over here, because then I'll have one equation that has just one variable in it, and I can solve for that. So let's take this equation up here, and I'm going to multiply both sides by 2 because that is my least common denominator. And that should eliminate my fractions for me. This is going to leave me with the magnitude of T1 times the square root of 2 minus the magnitude of T2, because that -1 times T2 is going to give me a negative T2 there. This is now equal to 0 because 2 times 0 is 0. And now I can solve this equation for the magnitude of T2 just by adding it to both sides. And that means that the magnitude of T1 times the square root of 2 is equal to the magnitude of T2. And now that I know this, I can take this expression right here and substitute it right there for my T2, and then all I'll have in my equation is going to be T1s. So let's see what that's going to look like. All right, and that brings me right here to this equation. Now, right here, the square root of 2 times the square root of 3 over 2, we can just change that to the square root of 6 over 2. Because we're allowed to multiply radicals together. Okay, let's add that 2,000 to the other side. Then we'll have the magnitude of T1 times the square root of 2 over 2 plus the magnitude of T1 times the square root of 6 over 2, that should be 6, is equal to 2,000. And let's multiply both sides by 2 so that we can eliminate the fractions. This is going to give me the magnitude of T1 times the square root of 2 plus the magnitude of T1 times the square root of 6, and this is going to be equal to 4,000. Now remember, I am trying to solve for the magnitude of T1, and these would be like terms, but the radicals won't let me combine them. However, I can factor out the greatest common factor, which is the absolute value of T1, and that's going to leave me with the square root of 2 plus the square root of 6. And now I can see that to solve for T1, all I have to do is divide by those parentheses there. All right, and that's going to give me the magnitude of T1. And since we're rounding to the nearest whole number, this gives me 1,035 pounds. All right, so there's T1. And now to get T2, all we need to do is we can substitute. And I will substitute this back in right here and solve this equation for T2. And then that should give me both of my answers here. Yeah, both the magnitudes of tension. There we go. That's what I was looking for. Okay, I need to make a little bit of room here. No, I don't. I'll just get a new slide. All right, my equation is, so here's my equation. And remember, I am going to substitute 1,035 here because this is the number that I just found. That gives me the equation 1,035 times the square root of 2 over 2 plus the magnitude of T2 times square root of 3 over 2 minus 2,000 is equal to 0. All right, let's multiply everything by 2. This is just to eliminate the fractions. This will give me 1,035 times the square root of 2 plus the magnitude of T2 times the square root of 3 minus 4,000 is equal to 0. All right, here's my variable. Let's add the 4,000 to the other side. And I can actually subtract this one to the other side as well, because this is a like term with that 4,000. This is going to leave me with the magnitude of T2 times the square root of 3 equal to 4,000 minus 1,035 times the square root of 2. And then to solve for its magnitude, we're just going to divide by that radical there. And let's put this in the calculator and see what we get. And if we are rounding to the nearest whole number, this gives me 1,464 pounds. And so there is my second weight.